How tall are you? What's the size of the screen you're watching this on? What quantity of vegetables are you going to buy the next time you go grocery shopping? If you go grocery shopping. These may sound like mundane, random questions, but they do bring up an interesting point. How do we measure things, and why is it important to do so in a standardized way? Let's imagine you're trying to bake a cake. In order to do so, you'll need a recipe, which is essentially someone who already knows how to bake a cake telling you how to do so. Now, baking a cake requires a lot of very specific steps. You need to mix the right ingredients in the right quantities and usually in the right order. You need to put the mixture in an oven at a certain temperature for a certain amount of time. These are all pieces of information you must have if you don't want the recipients of this cake to get food poisoning. To make sure everything is done correctly, we need some way of ensuring that all these values or pieces of information are understood the way they're meant to be understood. For example, the amount of flour, baking soda, or oven temperature you use must be the same amount as intended by the expert writing the recipe. And this is where we welcome you to units of measurement. In order to avoid confusion and misunderstanding, we usually use specific units of measurement to define a quantity. And what these units do is specify exactly how much of a quantity we're talking about. For example, let's say you're asked, how far is your school from your house? And you respond with 7. The other person will still be confused. 7 what? 7 paces, 7 blocks, 7 kilometers, 7 Cs. You see, the number 7 alone doesn't really convey all the information. However, if you were to say 7 kilometers, now you've given a complete answer with which the other person can understand your intention. And this is because a kilometer is a standard measure of distance. What this means is that a kilometer will mean the exact same thing to everyone. And that's why it can be used to communicate distance. And that's exactly why scientists devised an international system that uses an agreed set of units for the 7 base quantities, the SI units. The 7 base quantities are, of course, distance, time, mass, electric current, temperature interval, the amount of a substance, and luminous intensity. And for each of these base quantities, we have a defined unit of measurement, unless you're American. Now, how these measurements were defined initially is vastly different from the standardized definition we use now. Take the meter, for example. The first definition of the meter was that it was 1/10 millionth of the distance measured from the North Pole to the equator, which we now know is not very accurate. The meter is now defined as the distance traveled by electromagnetic radiation through a vacuum in 300 millionth of a second, because, they didn't want to complicate things too much. The kilogram was originally defined as the mass of 1 liter of water, which surprisingly still holds up really well today. But the definition was changed to make it more accurate, and it is now defined as the mass of a standard platinum iridium cylinder that's held in Sèvres, France. As for time, the second kept changing as the definition of the day changed. This was before we finally settled on the standard solar days that we use today. The second is now defined as around 9 billion periods of the radiation emitted from an excited cesium-133 atom. And if you think this is complicated, wait till the next one. Electric current. Now, electric current is measured in amperes, and the ampere was defined by scientists in 1890 as the amount of current that would deposit precisely 0.001118 grams of silver per second from the electrolysis of a silver nitrate solution. Simple, right? However, More accurate measurements later revealed that this current is actually less than the 1 ampere that scientists thought they were measuring, and is now defined as the current that, when flowing in two infinitely long parallel wires placed 1 meter apart in a vacuum, produces a force per unit length of 2 into 10 to the power minus 7 newtons per meter, which is just perfect. Now, let's talk about temperature. A number of prominent scientists, including Newton, came up with their own temperature scales before the Kelvin finally became the preferred scale for scientists in 1954. 1 Kelvin is now defined as 1 over 273.16 of the thermodynamic temperature difference between absolute zero and the triple point of water. Then we have the amount of a substance measured in mole, which is defined as the amount of substance that contains the same number of elementary particles as there are atoms in 12 grams of carbon 12. And finally, luminous intensity, which is measured in candela and measures the intensity of the radiation from a source. These 7 base quantities and their units of measurements form the base on which all other units and measurements are derived. Again, unless you're American. So a centimeter is essentially 1/10 of a meter. A minute is 60 times a second, and a gram is 1,000th of a kilogram. By adding these prefixes, we can use the units without having to deal with very large or very small numbers, and this makes working with these measurements a lot easier, especially where there might be complex calculations involved. So, does this mean that any numeric quantity or statistic used is a physical quantity? Are efficiency or color codes also physical quantities? Well, no. Being numerical alone doesn't make a statistic or depiction a physical quantity. It's only values that can be physically measured that are defined as physical quantities. So, for example, length is a physical quantity because we can measure it using instruments such as measuring tapes. Weight is a physical quantity because we can measure it using weighing scales. Time is a physical quantity. We can measure it with stopwatches. But things like efficiency and color and taste, they can't be physically measured and are only derived from other values. And this is the reason why these quantities don't have a standard unit and often vary depending on the values that they are made up of. The benefits and uses of standard units of measurement cannot be overstated. We use them in our daily lives to convey our ideas and to learn about the world around us. They're crucial to the work of people from all walks of life, and not just scientists, doctors, and engineers. I'm sure you can think of at least one time you've used any of these base units of measurement today. I mean, I'm sure you've commented on the weather today and said, the sun is so bright today, almost 3 octillion candela. No? Just me? Okay.